when we talk about the eye and the ear, okay, the whole point of both of these organs is that they have sensory receptors inside them. We've talked about the fact that your nervous system has sensory receptors all over your body. And those sensory receptors are in charge of picking up a stimulus. And depending on what kind of sensory receptor it is, it will be stimulated different ways. So your skin, which covers your entire body, has different sensory receptors in it that get triggered depending on what happens to the skin. Okay, so your skin has pain, cold, hot, pressure, and gentle touch. So at different layers in the skin, you have these sensory receptors, and if they're activated, it sends a message to the brain, and the brain reacts accordingly. Your mouth and your nose are linked. They are chemical receptors. Okay, they revolve with the chemical molecules in the air and in your food that brush over your tongue while you're eating or that make their way through your nasal cavity when you inhale. And those chemical receptors embed themselves into actual sensory receptors, and they get all excited and they send a message to the brain. Well, your eyes and your ears work the exact same way. And the actual stimulus that each of those responds to, when we talk about the actual eye, okay, when we talk about the eye, light goes into the pupil here. And if we're looking at the actual base of the eye, okay, so I'm not even going to draw, well, here's the cornea, here's your pupil, there's your iris, here's your lens. Okay, now, the really interesting part about light sensory receptors is that it actually depends on where they are inside the actual eyeball. So, we were talking a while ago about seeing in black and white. And in low light situations, you will not necessarily make out as many bright colors because there's less light, okay, in the dark. I mean, I know that sounds really moronic, but it's true. There's less actual wavelengths of light traveling in the dark because the dark is the absence of light. Okay, so in that case, your pupil actually gets really wide. It opens up a lot more. Your irises, the colorful muscle in your eyeball, actually retracts more and it makes the pupil behind it get bigger. And that stimulates the rods that are at the forefront of the eye. Okay, those are the actual organs that get stimulated. Now, if it's really bright out, the pupil will actually get much, much smaller. So the pupil will actually get much smaller and it will force the actual light rays to hit the back of the eye. And at the back of the eye, you've got this huge concentration of a different kind of receptor that actually can distinguish between different kinds of color. Okay, so notice how I'm drawing them all in color. These are your cones. They look like little ice cream cones. They're kind of like inverted triangles. And when the light ray comes into the eye through the pupil, because the pupil is so small, the light ray has less of a chance to actually expand and deviate all over the place. That's why the vast majority of your color receptors are at the back of the eye. Okay? And those little color receptors will actually get stimulated by that light, and they will send that stimulus all the way down the actual retina here, because the retina is attached to all of these guys back here. Okay, so the retina is at the base of all of these guys. And what they end up doing is they send that message down the retina to the actual optic nerve. And it will then send that stimulus to the brain. Okay, so this is light waves. Nothing is vibrating. This is just color, or the absence of, that is stimulating those sensory receptors. Okay, it's like when they're activated, they get bright, they get lit up. So if you can picture this big screen full of light bulbs, and when each of those light bulbs is a sensory receptor, and when they pick up light, they glow. And when they actually glow, they're wired to actually all feed into the main computer. The main computer is your brain. So they're sending that message, oh, I just got some light, I just got some light. They're sending it to the brain, and the brain is making the image. Your ear, on the other hand, is a wee bit different. And it has everything to do with the kind of wave that your ear absorbs. It absorbs a mechanical wave. It absorbs a literal vibration. And it's the rate of the vibration, okay, the amplitude of that vibration and the wavelength of that vibration that's going to determine what kind of sound that is. And your sound is very closely linked to your memory, because your brain's really good at saying, uh-oh, brain, have we ever heard that before? Okay, if we have, what is that? Oh, that's Miss Lupel's voice. Okay, so I better listen, because she's probably giving us a hint about what's on the exam. Okay? So what ends up happening with your ear is, as sound waves enter the actual funnel of the ear, yep, that's my ear, my outer ear right there. I drew it as a funnel because that's what it is. Okay? It's a full-on funnel. We go into the auditory canal. So here we've got our funnel that goes into the auditory canal. We can't see those waves yet. The moment we start to see that vibration is when it actually hits our eardrum. And the eardrum starts to vibrate at the rate of the sound wave. So if it's a really low sound, the vibration will be really big. If it's really low but really loud, then the amplitude on that vibration will be really big. And that sets off a chain reaction, because the next thing in the inner ear, or the middle ear I should say, that's actually hitting that guy is a bone, right? You've got your hammer here, right? And as the eardrum starts to vibrate, the hammer that's touching it will then in turn vibrate at the same rate. That hammer, okay, so here's your hammer. That hammer is actually touching an anvil. Okay, and the anvil will start to vibrate. That anvil is actually touching the stirrup. And that stirrup will then start to vibrate. And then we see, so far this is almost like a game of hot potato. Okay, or a game of like, pass the message. Everybody's basically passing the same message on. It's like playing a game of telephone. Okay? So the first one to vibrate was the eardrum, and this actually touches on the actual vestibule. And inside the vestibule, you've got a bunch of fluid. Okay? So you've got a bunch of fluid that's inside here. And if you've ever had a container of water and you've shaken that water, okay, the water will vibrate inside the container at the same rate that you're shaking it at. So as the little stirrup here starts whacking that bone on the side of the vestibule, okay, that vestibule, the fluid inside the vestibule will start to vibrate. That fluid is also inside your cochlea, which is that kind of spirally sort of bone. Sort of looks like a snail's shell. And on the inside of your cochlea is where you find your actual auditory nerve. So your auditory nerve is sitting there inside, and it actually gets really thick once it leaves the cochlea and goes to the brain. But the thin part here has these little hairs sticking up on it. These little tiny microscopic hairs. And they're immersed in that fluid. As the fluid vibrates, they start to vibrate at the exact same rate. These little guys right here are your sensory receptors for hearing. Unless there is a chain reaction of actually touching stuff and taking a sound wave and making it into a physical wave, these sensory receptors will not work. So that's why we have that chain reaction of something hitting something and something sitting on it and vibrating because of that. And then that then goes to basically the auditory processing center, which is very close to the brain, or to the ear in the brain. That's how sound is processed.